Thanks very much for coming. It's about 3 a.m. in the morning for me, so if I start falling asleep, just shout at me. This is a talk actually Ray forced me to put that together because he sent me to give a talk instead of him. So I just put a few things together which basically I've been on my background. I many years back I actually started a company which is still running in Princeton to do content routing based on XML. So because I've always been interested in network abstraction. So if how do actually developers use networks? And one of for me the big surprises was I went to a Microsoft developers conference where people conference there were writing distributed applications, and nobody there had any idea what a socket was. So developers don't use those, for them, very low-level abstractions. And we as network researchers still think that the socket is this sort of godlike structure handed down from the mountain and we can't change it. So what I've been trying to do is, and if you actually look at it, the internet, if you ask the common man on the street what the internet is, they give you a very different description of what it is than what network researchers are usually doing. And so I'll talk about a few things here. And before I do that, let me just start giving you one slide on NICTA. NICTA is a national lab in Australia. It's a center of excellence in ICT research. There isn't really anything here in Australia, in the US equivalent. We are a research lab. We're about 700 researchers, of which 300 are PhD and master students. And we're actually not we're not handing out any degrees. We are affiliated with about 7 universities, and those students actually come from those universities, and we may give them a scholarship. And they're working with us primarily on their thesis project. So we're distributed around 5 labs, 2 in Sydney, 1 in Canberra, 1 in Brisbane, and 1 at the...
So can you just give us another second? How does that really work? Like, do they do coursework for a year or 2 and then do thesis research with your...
Yeah, basically, if you do a PhD in Australia, most universities don't require you to do any coursework.
So you guys are all like...
It's European.
No, but also for the education system is slightly different. It's a little bit like the British one.
Yeah.
You don't do a master's, so you actually have undergraduate is only 3 years. Then, if you want to go any further, you do an honors year. So basically, add a 4th year, which is a special year. And then after the honors, you can go straight into the PhD, which is only 3 years. So it's actually much shorter, and that's why we actually have a lot of problems, because we get them in way too young, and then we only have 3 years to get their PhD. So it's fairly compressed. So that's why we can similar situations.
3 years, the students come to your lab in year 1. Like these students who are not only students of some university, one of your 7 universities, they come to your lab in year 1 of their 3 years?
Yes.
And who actually does the real heavy lifting of the advising?
We do it. So most of us, we have what is called a co-joint appointment, where we can actually be, we're not employed by the university, but we can be official advisors. So we have essentially the same rights as the academic staff. In some cases, it doesn't really work practically, so they have an academic, then often they have an academic, like a professor from the university as their official advisor who hardly ever sees them. But most of the basically all the supervising is done by us. And some of them, it's a little bit of a problem because we're actually not at the...
recruiting the students, or the schools recruiting the students?
Both of us. So they have to apply to the university for admission, and then then depending on, and then we usually have a meeting together on figuring out about the scholarships. So they often end up with 2, 3, or 4 scholarships. And
so
some
the students who end up working in your lab are paid through scholarships your lab provides?
That's correct.
And so eventually it comes down to who's paying for the, who's doing the financial support.
That's correct.
All right.
Yeah, so the biggest difficulty is then always the intellectual properties, which is usually it's always the same story. Yeah, so that's so old numbers, but this lab is actually right on campus. This is right on campus. This is just across the street from the campus. This is on the border of the campus, and we're the only ones about 10 minutes walk away from the nearest campus of the reflective universities. And just to complicate things, we're a commercial company, but we are owned by 2 universities and 2 state governments. And 90+% of our money comes from federal and state funding. So we're doing research, but we actually, the focus is on use-inspired research. So we only fund research projects where there is at least an explainable story on how that can actually be useful for somebody.
And WINLAB doesn't meet that standard. Are you contrasting that to other?
No, it's basically, we're using that as a contrasting ourselves to universities, because universities should really be more like blue sky, and we shouldn't worry about that one. So we can't, being paid, we actually, half of our funding comes from the Australian equivalent of the NSF. So, and that's why we have like 2 masters. One is sort of the NSF-like, and the other one is the Ministry of Industries. So those guys only interested in how many jobs we create directly or indirectly, and the other ones only care about how many papers we publish. And so we're a little bit in the middle. But most of our outcome is not really. Most people are not really thinking themselves as much different as being at the university. Just no teaching load. That's pretty much the advantage. But we have spun out a couple of companies now. If you have a mobile phone with a Qualcomm chipset in it, it's most likely runs our microkernel. So our microkernel is at about 600 million phones by now. And if you go to a large rock concert, it's most likely that if you don't see thick amounts of cables, we have now a company which provides audio equipment. Basically, all the audio for large concert goes over Ethernet. So basically, they run everything over an Ethernet network, and that's being basically sold through most of the large audio equipment manufacturers. Okay, so let me get into what I want to talk about. So what does it take to move all that stuff we now doing all the conversions? What does it take to move that onto the internet? So if you read the trade magazines, basically everybody is complaining that the core of the internet is going to be overloaded if we put all the TV channel, all the video on it, that the core of the internet is melting, and we need to spend billions of dollars on Cisco and Lucent and whatever gear to increase the capacity of the internet. Now, if you actually look of how much of the traffic going through the internet right now is actually real time, meaning that it really needs to go across the network at that time, it's actually a very small fraction. This is sort of taken from a Cisco report. It's less than 10%, which you can think of as truly real time, and that is like video conferencing, VoIP, and some portion of gaming, which is basically the control traffic. All the other rest is due to traffic, is due to non-real time. By non-real time, I think about the YouTube and music that really doesn't have to be streamed over the network at that time. At the moment, we do it because that's how we build our applications. So, but as far as the network is concerned, it's really has to be shipped across right now, because the only thing is, as far as the network is concerned, is it's just a CISA packet, and it's being expected to deliver that as quickly as possible on the other side. So, and the question is now, is that primarily because that's because that's all the abstraction we have to the network? That's all it actually provides. So we have some kind of packet with a header, and most of it is IP, but it can be something else. And there's only one way of shipping it in, and then based on that header, it's just supposed to pop out somewhere as quickly as possible. But coming back to developers don't really think in packets. You know, this is sort of our UML diagram. Information isn't really necessarily captured in packets. You have objects and relationships between them. Do you remember who this guy is?
You know, it's funny. I read a blog where they always use his photo and say approved by, and it's is it Rip Torn? It's a famous actor who was picked up when he was drunk, right?
No, this is actually the Unibomber. This is the. Yeah. So I think so. Yeah, when that I think that's when they picked him up in the cabin. Pardon? Maybe not.
I have to go look. And do you think he's not the Unabomber, or you're sure he's the Unabomber?
I'm not 100% sure. When I think I picked it, I thought it is.
Pretty sure.
Okay. So, but coming back to what goes across the internet. This is a slide taken from an Australian presentation. Like, this is our Australian, the different TV channels. But even if you replace that by the American channels, I don't think it changes too much. So basically, more video was uploaded to YouTube in the last 2 months than what most broadcasters have broadcast in during their entire existence. You know, Nokia is the largest camera manufacturer in the world. So most of the content actually generated right now is actually most of content generated is actually generated on mobile phones. And especially now with video coming along, it gets even truer. The gap is even increasing. Okay, I don't have to go about that one. That primarily everything is content. So how do we ship content around in the network? Okay, beside IP, what has the research community come up with? And primarily, in WINLAB falls into that part with the store and forward. It's what I call sort of named objects. You have a sort of a bag of bits, and you attach some kind of label to it, and then you come up with ways of more efficiently kind of ship that around. So you have a whole lot of different approaches on how to deal with it. But what about the metadata? This is again just, you know, file like bag of bits like files or songs, and all of them are identified by a label, all the peer-to-peer stuff that goes around that one. But what about metadata? My example being a parent is that, you know, I go to the school functions, like little kids giving sort of concerts, and all the parents come with cameras, and inadvertently when your kid does something cute, you don't have the camera ready, it's just like broken, or you have switched it away. But pretty sure there's like any of the other 50 parents there has recorded that. Now, there's really no way of me really to capture that one, or besides just walking up to somebody and asking them. But now with face recognition and all that one, it's actually relatively easy to automatically get a lot of metadata out of pictures, we've been developing some face recognition technology where you can actually get you can recognize robustly faces with relatively, basically out of security camera feeds, with just like 12 pixel across the head, and you can very robustly find faces and identify them. So, giving you a picture here and another one here, and you know, there's this Jim's mom took this one, and this is from the same event. And over here, we identified Jim because obviously his mom's phone has a lot of pictures of Jim. But over here, Mary's dad we've identified Mary here, but he doesn't really care who that is. But if you ultimately have, if there's all being connected, it's pretty easy to actually identify Jim, especially if you use this sort of social context that both of them have kids in the same school and it's around the same event. So there's a lot of things we can do in basically mining information out of social network-like environments. So if we now want to do all these applications, which the Flickr and the YouTubes of this world are going to do, is there anything anything the network community is bringing to the pictures? And again, if we only have this sort of bag of bits with a label, then we cannot really capture any of those relationships. So let me quickly run through networks again, sort of to give you an idea of how this all fits together. Obviously, most of it we sort of know this host-based one circuit with packet switching, unicast with multicast, so that's actually telling you anything new. Then there's this whole group around publish-subscribe. Are you familiar with publish-subscribe networks? So the publish-subscribe is basically that it's sort of a more loosely coupled communication. You just publish something, you don't really care who to send it to. So you just throw it out there and you put some labels on it. Either you sort of publish it into a topic. Think of cable TV, or just basically add a channel and you just publish it on that channel. And if you want to receive something, you just subscribe to the network. You either subscribe to a channel, then you get everything which somebody else publishes to the channel, or you can get a bit more sophisticated, that what is being published actually contains some metadata, and then when you subscribe to it, you kind of provide some kind of query or some kind of filter specification, and then you only receive those published messages where the metadata associated with the published message basically fits your filter. And what you have now in what's often referred to as the enterprise bus, which is sort of now a design principle for many of enterprise applications, which is primarily using sort of a channel one that applications or services in an enterprise publish information to a channel or to a topic, and then other applications basically pick that up. Amazon.com primarily runs on this abstraction that when you go to a website, when you go to Amazon, if you look at the website, there's lots of different pieces of information which come, and they're being sort of collected through a publish subscriber, through an enterprise system, where they basically publish that this person is interested to buy this book or this topic. What other entities in Amazon want to basically sell you something, and so you can dynamically fix that together. And by sort of loosely coupling, you can actually add new services very easily without having to break the entire thing. And what I've worked for many years was basically based on XML on a tree abstraction, where the metadata is basically an XML fragment, and then the subscription is more like a tree-based query language, like XPath. Now, coming back to the problem of primarily saying that most of the traffic on the internet is related to content, to media. There we have companies like Akamai and LimeWire, which have built basically an overlay structure over the current internet to help large media companies to efficiently distribute their content. So if you go to CNN.com or Disney.com or Apple, you don't get most of the content, most of the images you see are not coming from those companies. They're actually coming out of those CDNs. But again, they don't really care what it is. You give it a URL, and they just look it up, and they give you back that bag of bits.
Max, so
yes.
at a high level, the problem we're trying to solve is distribution of content on the internet. Is that
the focus. He isn't straight yet.
Yeah, I'm sort of going. I'm sorry, I'm meandering a little bit. My 3 a.m. is kicking in. I'm not as coherent as I would like to be. Let me get to the point here. So this is what basically the Akamai is. It's sort of the content distribution. But my argument here is that that application programmers don't really think about this sort of file abstractions. If you write applications, if you coming back, if you remember those pictures, if you're trying to do metadata, it's really about identifying relationships between entities. If you write object-oriented programming, or even with structures, you basically have some kind of entities, and most of the information is actually in the relationship between those entities. So it is much more than just like independent entities. And if you actually think of if you look back at the basic algorithm behind Google, Google initially completely threw out this idea of trying to semantically understand web pages. They just looked at the links between them and said there's an incredible amount of information in the relationship between entities. And even in our, if you think about language, it's not just about, we're not just having nouns, we actually, the verbs, the predicates which relate different nouns together. That's where most of the information lies. So if we now, as a developer, work in this world, however, the system, the operating system and the network really only support this sort of bag of bits as a label. Think of it, the packet is not really that different from what you write on a disk. The basic sort of building block on a disk is a block which has an inode. Is it inode? Inode. So it's basically a block with some ID. A packet, an IP packet, is some kind of is an array of bits with some kind of label. That's the only abstraction we have down here, but this is the abstraction that the developer, the application and service developers operate. That is a very different abstraction from what we provide down here. Now, those guys here have been not really they've not really trying.
So the developers up in the green circle level, do they have sort of software tools that let them just think like this?
That's correct, and that's what we have. That's what middleware is. That's what normally middleware is. On the sort of database file system, we have something which is called ORMR, Object Relational Mapping. It can take this object-oriented world and it maps it down to either to relational databases or to low-level files. And if you think about all this RMI or remote RPC mechanisms and remote method invocation in Java are actually now software blocks which basically make this lower level, this distributor level, this persistence layer more appealing to developers. The problem is that essentially those blocks take away a lot of information which could be useful down here, because they can only work at the abstraction this lower level gives. So now, if most of the developers are actually operating down here, why can't we bring the lower level abstraction up to here? And if we do that one, first of all, we can get rid of all the middleware layers, which for me is always, one definition of middleware is basically middleware fixes all the things the networking guys and the operating systems guy didn't get right. But if we now bring it up to this one, we now have a different abstraction, and essentially an abstraction based on so the abstraction now, which would be useful for the application layer, is what do they need? They basically need some kind of persistence, because a lot of the code, if you write code, a lot of the code is actually about persisting state, writing it out to a database, writing it out to a file, and then having additional code which basically brings the whole stuff in. And then communication with others, sort of often it is very loosely coupled information that you basically want to send some fragments of your internal state, which again is objects and their relationships. So then you either use middleware to help you there, or you have to handcraft what's often called marshalling code, where you actually take this sort of data structure and serialize it into this string of bits, and then send it over to the other side where you're basically trying to put it together. Now, if the networking and communication abstraction would A, support consistency and support relationships, you basically could think of this as what we call a global graph. So the network is persisting this global graph, and publishing events will essentially be just adding things to that graph. And your subscription would essentially be subscribing to some kind of subgraph. So essentially, you can use now this thing to map. You can also think of it that now allows you to map your internal state onto some global graph. And on the and you can now easily build distributed applications by other applications and yourself, basically synchronizing the internal state with state embedded in that global graph. So if somebody adds something through the subscription, you be informed back. So this basically has loosely coupled communication. So you can do synchronous one. It gives, when you publish it, it immediately comes back. Or you can have asynchronous communication that, because of the persistency of somebody else publishing it, later on when your application starts up, you actually get all the history of what others have added to it. And yeah.
What is the link information, and is it universal across all applications?
Yeah, so let me get to. So in order to do this, we don't have to invent anything new. There's a couple of standards out there which we can use. Basically, semantic web standards. If you're familiar with that one, there's a standard called RDF, the Resource Description Framework, which basically is a way of describing entities and the relationship between those entities. And there is semantic web also defines a query language for essentially graph structures, which is called Sparkle, which is basically a way of querying a graph structure. So we can use that those standards to do that one, and then the semantic meaning of those entities and their relationships is defined through an ontology, which is not embedded in the network, but is basically an end-to-end property. I usually compare it, think of it as the telephone system. You can call pretty much anybody in the world now, but you can only have a meaningful communication if you both speak the same language. But the telephone network doesn't care what language it carries. So here again, the graph structure, the graphs themselves have just labels. The links are represented by labels, but the semantic meaning of those labels is basically defined through ontology and has to be then basically agreed upon the communicating partners.
So, at a broad level, are you suggesting that the meaning of what is carried over the network is interpreted by the end host rather than the network itself?
That's correct. So the network itself only supports that abstraction of maintaining a graph. And the nodes themselves are just identified by labels. And we're using UUIDs, 128-bit labels.
And this is useful because it's easier to develop these content distribution applications, is it?
Basically, through that one, you have now a common abstraction to do distributed applications. You don't have to worry about how you now package things up and make them appear on other places. So you don't have to do the marshalling thing. It has persistency. So if you add something, it actually stays there. So you don't have to worry about persisting your state and basically again marshalling down to files or doing some translation between the object state and if you want to use a database, basically doing the mapping between the object space and what you need to do and how to translate that into relational abstractions. And basically, so if you do that, there's no need to synchronize devices. So think about all the problems we have now of keeping state consistent across the many different devices we have. We actually don't need YouTube and Flickr if you think about as them primarily providing storage. You can take this further. A lot of the services on the internet we have right now is basically services providing storage and providing essentially asynchronous communication between entities.
For example, I'm trying to understand how is it different in the sense, reading the case of YouTube, it's providing two things, storage and search. YouTube provides a storage,
Yes.
and maybe a search.
That's correct.
So that's what you're also saying, that the system has to maintain a persistent storage within itself. So when the question comes that if you have a network where you have to have a storage, who's going to maintain the storage? Because it's
the same people who provide the networking.
Yeah, but I think in a way the field is evolving in a different sense, in the sense that there are private companies which are providing the storage. Now, for all practical purpose, you can think them as a networking. There's no need why those people who are providing you the communication should also provide you the storage. Again, it could be at the end.
But there's no need to do that. You're right, and it depends on how you deploy such a service. So in our current way of the way we think of deploying it right now is actually as an overlay service. So you can use like Amazon's storage cloud and all that to basically realize that. So there's a difference between actually who is providing it and what's the best way of providing it, and the abstraction or the overall service. One of the main reasons we're thinking about that one is in the fixed network side, it's really there may not really be much reason to tinker with that one because of the cloud computing model works there fairly well. However, on the mobile side, I believe that the cloud computing abstraction doesn't work because the wireless link will always be the bottleneck. So having this idea, cloud computing works if you essentially think of having an unlimited, like an unlimited big pipe between you and the cloud, and basically the nearest Google data center or Amazon data center. If you don't worry about that link, then the world is good. But on mobile devices, that will never be the case.
Will it never be the case?
I believe it will never be the case.
Because it all depends, because there is a particular kind of computation that you want to do. It will be more energy efficient to send it over a wireless link and then let the cloud computing infrastructure do the computation rather than doing it locally. Because here in the mobile thing, we are not only worried about the capacity of the link, we are also worried about the battery power.
Yes, but the
it most likely, it won't be the same model as we do it with wired network. I agree with it. But I'm not sure it always is the case that doing a computation locally is much more a better option. So you eventually go down to this cloud computing infrastructure.
There's two things. I agree with you that locally computing everything on a mobile device is not necessarily the right thing. But the progress there, if you look at the technology roadmap, is actually much more aggressive than on the networking side. The other thing is, and which is what I'm sort of trying to go primarily, is that many of our applications right now are actually not really time sensitive. Meaning that things don't have to happen right at that point. And right now, the abstractions we have at the lower level don't take time into consideration. If you present something to the network, it doesn't know that it has like an hour to get it over to something else. It just basically it feels like it has to do it right now, even if you're in a bad spot. So being able to actually exploit time, that there are a lot of applications we have right now, and a lot of the data intensive one are actually quite delay tolerant. And so we want to capture that one. The other thing is that a lot of the communication, especially with the mobile space, is actually relatively local. So you don't have to ship it across long distances to get it somewhere. But that's like the most of the depending on how the infrastructure is set up. But if you actually look, check of the amount of local storage which is being sold even into homes, people have incredible amount of storage capacity in their homes. Not everybody is uploading all their pictures to Flickr. A lot of them have them spread across the different computers they have in their homes, and there's an awful lot of traffic created by all the different synchronizing agents running on your different devices. Now you can argue that in the home you may not really have a wireless capacity problem, but actually in some homes you do. But again, my argument is that the primary argument is if we actually raise the abstraction, the service abstraction between the application and the providing infrastructure, we have, by raising it, we get a lot more design space. And then we can optimize it within that much larger design space. And it may turn out that in certain circumstances, the easiest way is to just basically use the classical cloud model, where you basically, whenever you get something, just ship it across the pipe and into some big cloud computing facility and just keep it there.
So my last question, which is about, so I understand your point that the current network does not understand the difference between latency sensitive data packet or non-latency sensitive. But in this new architecture of publish and retrieve, how are we going to support applications which are actually latency sensitive?
Which are latency sensitive. Now, the publish subscribe doesn't necessarily mean you cannot do those.
Yeah, but what are the abstractions?
You can actually do the same abstraction. If you look at Van Jacobson's, what is it called? The standard. He actually runs VoIP over. So he actually runs a VoIP service. He has basically shown that you can run VoIP over it. Most likely not necessarily that efficient, but it's doable. And essentially, if you actually add metadata to it, you can actually you can tell the underlying service realization that this is actually latency sensitive stuff, and you better get it over to the other side. And you can through that the subscriptions are actually persistent. The subscriptions themselves are persistent as well, so you can actually use that information to already set up the whole infrastructure so that you can also preset the path and everything. So it's not necessarily my primary interest is more like the non-real-time stuff, because that is huge and that is growing much faster than the other thing. I'm not necessarily at this stage. I'm worried about having a unified solution, but I don't see that it couldn't be that. And given that it's actually a relatively small fraction, you may not really have to implement it that efficiently as long as you can stay within those latency bounds. Even when you think about it, for instance, one of at the moment, people worry the most in latency sensitivity is games. Those massive multi-user games. But even there, all the data they're creating on the network, even on those games, there's the fraction which is really latency sensitive is actually a very small. Most of the data is actually consumed by shipping like texture files around and avatar information and
I think it's mostly voice.
But
It's mostly voice. Because all the kids who play those games are always talking voice as the other kids playing.
yeah, but
Yeah, with keyboard and mouse, there aren't that many bits. I mean, it's Maximillian, there aren't that many bits in keyboard and mouse manipulation. So there's some images that they blab all the time.
yes, but actually the voice itself doesn't actually it actually doesn't make up that much.
Well, it's like 20, it's 10 kilobit per second, right? But I don't think keyboard and mouse is 10.
No, that's.
I mean,
Oh, by the way, Adobe just went online with a voice service last week in China, supporting 800,000 simultaneous calls. So trying to the advantages of such an abstraction is that I now extend communication not only in space, which normally it does, but also in time. So it also the same abstraction also supports asynchronous communication, and do that through a single model. It captures the
so all those old things, though, just publishing systems, right?
Mm-hmm.
Whether it's Flickr, any Facebook, they're publishing systems for expressing your content, right? So somehow in your new world, you say just publish. Well, what does that mean? Is it just like RSS, kind of like you don't publish with any, you let the subscriber figure out what it should look like?
No, you're publishing in this model means you basically add information to that graph. You either add new nodes to that graph. Think of it as the abstraction as being this one humongous graph.
Yeah. Actually, could we take a concrete example of Facebook just to be on the same page? How this would work with your
Oh, Facebook, okay, now you catch me because I'm not I'm supposed to have a Facebook account because my son has one. And
or any of those ones on the
no, just think of it as basically a node can be a person, a node can represent a message, I can represent a picture, can represent a geographic location, and then basically, this node represents a person, and if this is like a message, let's think like email is a simple one, then this link may represent that this person is the sender of this message. This person is the recipient of this message.
But this graph is still stored at a central location at
No,
Facebook.
don't think that it's internet. It exists inside the cloud, inside the network. Where it's really stored, we don't care.
But Max, I guess my point is that when you publish, you make nodes and add edges to the graph.
You just add things to the graph. Yes.
Right, but you know, in this kind of soft world, there's choices about what to add. Right. So right now we use software like Facebook, or you know, they essentially help you sort of add to the graph in some. They don't call it a graph, but you're adding to the graph in a way that they help you add to it in a way that makes sense to other people.
Sure.
And Google Reader, right, is actually just reading some version of that graph to make sense of it for me, right? But I guess the question is, like, it seems like as soon as you say, well, add to the graph, then you need something, right, that kind of helps you. The graph is too big to.
No, I'm not saying that this will basically replace that you don't need any applications anymore. You still then have to build an application on top of it, which makes it for you as a user nice, that you have like nice GUIs and you press buttons and you type something in and you sort of like press the send button.
No, I'm saying even beyond that kind of notion of the interface, right? It's the how do you choose to add to the graph? Like it's not you know. There's that's adding to the graph is not so well defined, right, to my mind.
I think what Roy is saying is that the sender and the receiver in the traditional notion have to have the same idea of how it's supposed to be added to the graph.
No, you have
so
to.
that you can express a query that will actually find that information.
Sure, but if you now, let's stick with email as a simple example. Now you still have an application there where you like type something in and you select, like from an address book, and you select who you want to send that message. But then when you then press the send button, what the application does, it now tries to it basically, the sender, like yourself, is identified by one of the nodes in that graph,
Yeah.
and the recipient is identified by a node in that graph. And most likely the way your address book works is actually doing a query on that graph to get your state back. It doesn't have to store your address book locally. Your address book is in here as well. Because all your friends are identified by you, and there's a link to them and saying they are my friend or they're my colleague.
So who defines the format of what a person node looks like in this graph?
So again, that's basically
the
then
email application specific.
that
And
is
every
application.
application there will be a different person description.
Either application or domain specific. I would sort of go away from the application. It's domain specific.
So by domain you mean all
By
of
the messaging domain, we have now very well established ontologies in how to describe people, the friends of a friend ontology. There's something similar. There's already a lot of work done out in that one. And also there's also a lot of work done on if some applications which are in the same domain use slightly different ontologies. We actually have now pretty sophisticated ways of actually merging the ontologies automatically. So you can have now like little reasoning engines running around here and basically trying to fix that graph or adding new relationships to that graph. Basically saying that you may end up being identified by more than two nodes, more than one node in there. So then you can have some reasoning engines or some agents which basically then looked at and saying those two should actually be the same.
So do you think this makes privacy easier or harder? I'm serious, because like actually in some ways, if you really define everything as this graph, then is privacy nothing more than keeping some edges secret? Like essentially not in some way limiting the knowledge of the existence of nodes or edges.
This is an argument I have now with a couple of privacy people for a while. Is that in a way it looks like it makes privacy much worse because you have everything out there. On the other hand, I think it makes privacy easier because you can think of privacy or basically as an access control problem, as a filter. There is this global graph, but what you are seeing is essentially a filter over that graph. And now you actually have a single place where you have to worry about what to reveal and what not. The classical problem we have right now, like in enterprises with all these web services. So essentially now you have in enterprise, you have now many entry points into your internal data stream. And at the moment, we're only securing each of those access points individually. But that now makes it quite easy for somebody if they come in on different one and taking the information and then actually combining that. Because the enterprise itself doesn't actually have a single picture of what of its internal state it actually gives out to a particular person or particular entity. Here you have a single. Here you keep all the information you have, and you basically define on what your access control. Think of it as an additional filter. So that can hide nodes and can hide relationships. Now, how difficult is it to then run again the same inference engines and over it and basically add those nodes? That's a different story, and that's a very huge research problem.
Considering the size of the ground, doesn't that make query really hard?
But that's what a research, very interesting research comes in. I'm saying this makes it easy. That just poses an awful lot of very important research questions. Yes, if it's very big, but then there's also most likely quite a bit of locality. Those graphs are not. They have some strong locality features. So we don't really know yet. I'm surprised that nobody has picked up something I usually get. The question is, I don't support a delete function here. You can only add things, so it will just grow. Because deleting things, in those huge structures, is just basically a nightmare. Now that may actually run against legislation, because there's legislation around there in certain places that you actually have to delete things, be able to delete. Like in medical databases, you actually have to be able to delete things, and not just delete it in the database, you have to delete it in all the backups. Which nobody knows how to do that. Pardon?
Most companies want to delete their records as soon as the law allows them to.
Yes, that's the other thing, yes.
That's a more general question. If you look at this graph, in a sense, it's a large set of global state programs, so global data structure in a sense. If you look at the history of software engineering, that's kind of how programming started out in small programs, and then the key insight in the software engineering domain was you don't want to have big global data structures. You want to do information hiding, hide your data structures behind programming interfaces, so that the data structures are easy to change, because they often have to change as software evolves. And that's all about, say, object-oriented programming and the work that was done before that. How do you square this up with these key lessons from software engineering?
Yeah, actually, I think that the primary driver, there's clearly something with data structures, but we had even operating systems which were basically maintaining state, so you could crash them and you can bring them back. Or, why do we have file systems in the first place? That seems to be a pretty silly sort of a pretty low-level abstraction, why don't you just persist data structures? And there were attempts in operating systems that you could basically, freeze a program and then restart it with the same state in place. The primary problems there was that we couldn't keep it from growing because there was always bugs in it, and it turned out to be much easier to solve problems by simply resetting everything and starting from scratch. The operating systems, one of the biggest problems of those persistent operating systems, that they just got bigger and bigger and bigger because we couldn't collect it, we couldn't cleanly collect garbage. Now you can argue that in this world of pretty much infinite storage, you may not just worry about that one. You get an awful lot of junk. And actually, what I'm saying, I don't want to delete anything. What I'm really interested in is like an abstraction of where we can actually take the soft state we have in networks. Can you actually apply that to storage as well? That you add a node and a link, but there is actually no guarantee that it will be there when you ask for it later. So it's so that way you may have a natural way of basically getting rid of things which is not being used. It's basically decaying, and if you really care about it, you sort of have to periodically refresh it. With sort of a high probability you find this stuff.
So deleting is one part of.
But you are coming back to the.
So what's the best programming interface? It's a global data structure. There's some analogy to how you organize a simple program. You make all your variables global, simple global data structure, and every function accesses it globally. Or do you do information hiding? Hide every variable as local as possible to make it easy to change. And
yeah, but
if you look at the history of software development, the answer is pretty clear there. And the only exception I can think of, and that might be the one you want to study a little bit more, that has been successful, is of relational database systems, which also give you the impression of the one big global data structure that every program queries.
But the main reason for in the object-oriented world to maintain the data structure internally is primarily driven by implementation, because the reason you often change those internal data structures is because you're changing the way you implement.
The program requirements change.
Yeah, but it's not look, even object-oriented doesn't have a silver bullet, because it works if you don't change your API, if you don't change your methods. And as soon as you start changing that one, you get basically back into the same problem. So if the API is in a way a representation of the state and the operations on that state, you basically want to reflect to the outside. So having said that, that doesn't necessarily prevent you from, in a way, keeping state here, which is essentially only internal to the way you want to do something. But yeah, it's the whole notion of having sort of large graphs and doing that one, and that's why one of my main running discussions with our software engineering group is I don't really believe in the service-oriented architecture. So here, this is basically what I call a state-oriented architecture, and we have very good arguments either side of why it's working and not working.
So where does this database exist? Anywhere, everywhere?
Everywhere, anywhere.
But how do you have sort of consistency? So it has to be, it's not all in one database, clearly. So how do you sort of get consistency of it then?
So basically that's the, there is what we call eventual consistency, That's basically the database. Pardon?
Should I ask what is it?
Eventual consistency is that the only thing you can guarantee is that if you stop adding things, sometimes in the future everybody will have the same view. If you stop adding things and if you wait long enough, everybody will have the same view.
So somehow, like, these links then, I mean, in some way, like, somehow one database can't have every object in it, right? Eventually you have to say, well, I have some kind of a database entry that says I have something here that's linked to something over in somebody else's in a database somewhere else. Does that somehow have, does that have a way of being named over there somehow? And then do other people have copies of this?
But now you're talking about how you implement it.
This is trying to understand what it is, that's all. Maybe I can't separate how to implement it from what it is, but I just sort of figure,
The notion that Max has in mind is probably quite similar to that of what you have with web pages right now. You can look at your set of HTML files as one large database that's cross-referenced across multiple servers, across many servers. And it's not perfectly consistent because you have broken links as you know.
You agree with that? So, okay, that makes sense. Do you agree with that?
Yeah, so it's basically, think of it as, we're using, for instance, at the current implementation, each of the nodes and the links are identified by a label. We're using 128 bits to identify them. And we're essentially, so the basic, and maybe I should go to this one. So this is our packet. We still have a packet, so networking guys are happy. So our packet is essentially, we have our basic storage, our basic building block is a 5 tuple. So we have from a graph point of view, it's a subject. It's like the two nodes, because in the RDF speak, it's subject and predicates. And then you have a subjects and objects, and the predicate is the link between them. The link is a named, if you're on the graph, it's a named link. Then what we're really representing is a hyperlink, is a hypergraph, because each of them is identified with a context, which itself is an addressable entity. And then we forget about that. But then we have a timestamp, because timestamps are actually quite important for ultimately maintaining that eventual consistency. So this is the primary thing. And if you just think about the subject, predicate, and object, and you think in the simplest case 128 bits, so basically if you just concatenate them, you have an address. I have a big number, and at the moment we're using a DHT to store it. Now, querying DHTs this way is a bit tricky, but that's it.
So let's assume a hypothetical situation, right? Let's assume a hypothetical situation that every person in this world has a Facebook account.
Yes.
And all kind of content, video, photos, text, etc., are uploaded onto Facebook, are shared via Facebook. Okay. So would Facebook be doing what you are trying to do here? Like, if that's the case. Like, even in Facebook, each individual is a node, and each individual is sharing some content, and some other individuals are interested in your content. You can have filters as to who can access your content. It's not necessary that all the content you upload is immediately seen at, say, if I upload it here, it's not necessary that a person in India sees it a second after I upload it. There is some delay, right? All those issues are there, right? So other than the fact that today you have Facebook, Orkut, Flickr, many kinds of services that are basically, that seem to be providing what your abstraction will provide. So is there any difference in having one single abstraction across the internet and having these many private companies or private firms or whatever organizations providing the same thing and having their own set of users?
But first of all, in the social network space, we already have the problem right now that, okay, now Facebook is sort of almost trying to take over, but actually is not really, if you think about all the billions of people in China who don't have a Facebook there.
Yeah, so that's why I said let the hypothetical situation be that everybody has a Facebook account. That you could argue that that's a good thing that not everybody only uses Facebook, right?
The thing is, from a user point of view, there's no difference. Okay. Now, from how that's being deployed and realized, there may be a big difference because now, right now, Facebook has to provide all the infrastructure to implement that, and they basically do that through big data centers. While if it's basically now a network abstraction, and there's a lot of locality in those ones. If you look at Facebook, there's most likely quite a tremendous geographic locality. A lot of teenagers are characterized, their circle of friends is actually very much tied to geography. So by having that one as a network abstraction, you can actually now do a lot of optimizations on how to provide the service, where do you provide the different parts of the service. You could do it through a classical cloud, but you could also provide it through local storage. And right now there's a lot of realizations from the media company side, from the media side, that actually ISPs may be the best way in the future for actually selling a lot of the services, because an ISP already has a billing relationship with you. So now, and the other argument which we're making to the carriers is that with an abstraction like this, it's the problem, especially with the mobile carriers, that they went all the way trying to actually become the next business of the world, and that failed miserably. But on the other hand, who knew that AT&T had a crappy mobile service before the iPhone came out? But a lot of the problems we have now, especially on the capacity problems with mobile networks, wireless networks, is because a lot of the applications are basically choking the network at a time. You don't have that time to play. If you actually look at the traffic, the capacity usage in those mobile networks, you actually see that there are huge gaps where there's not much going on. And currently we cannot use those efficiently. Nor can the carriers use them efficiently. So if there would be a slightly higher level abstraction which allows them to play with time and shift things around, you could do an awful lot of optimization. And with it, you can actually reduce the cost of providing those networks dramatically. So let me just wrap it up. So at the moment we felt that we realized that mapping them onto a DHT, understanding query, how to use Sparkle, but Sparkle is quite a big thing. So at the moment we limited ourselves to a sort of a tuple pattern, and for that we implemented the read algorithms and in a distributed way. So we're just writing up a paper on that one. But as I said, the big problem here is in a DHT is because we actually we want to do a multi-dimensional query with wildcards, which DHTs are actually not very good at. Okay, and so we can actually deploy this today. As a simple case, it would be as an overlay using just the Amazon cloud or WINLAB if you don't really care if it works or not. But also remember that a lot of networking services, new networking services, actually started inside companies. They actually deployed first inside companies or inside campuses and then only grew outside. But the carriers often didn't get in the first place. The carriers initially just provided the basic plumbing, but then when it sort of really grew out of enterprises. If enterprises wanted to connect to each other, then the bigger carriers came into place. Or even can start inside a single application. We're now talking to Dolby. Dolby is quite interested in figuring out on how to manage all the media inside a home or across families and extended families. And they're quite interested in using that. So you could just start inside a single application. And, so there's many ways of getting something out. Essentially, you don't have to start from day one to replace all the Cisco switches routers in the world. So obviously, we're not the only ones in the world. There's actually probing around for a long time. We couldn't really find much, but actually it turns out that Europe has a huge amount of EU projects in terms of the semantic web space, sort of around web services, not really so much in the networking side, but there is this triple space computing initiative, which is they're coming out of the they're talking more using more like sort of grid environments, but they're talking about very sort of doing that distributedly. So this, and interestingly, the database community is actually, if you look at it, the database community is more and more encroaching on the networking space. There's a lot of networking, interesting networking done inside, coming out of the data. So the whole sort of distributed eventual consistency. If you look at some of the large, the database community is desperately trying to get rid of the asset of this really strict, always consistent ways. So unfortunately, the new acronym they coined is also called ASSET. They just put different names to the acronym. But the way, like Google, Bigtable, Facebook, what is it called? Familiar? No. So those companies which have huge data, essentially huge databases, they are going away from the classical relational database things, and that's sort of more like table structures which are sort of loosely and then split, and ultimately if you add something, eventually it will show up in all the other copies. So you don't have a guarantee on how quickly it is, but all you have is that at any given snapshot, at least it's in itself consistent. But it may not be the same across all the different things. So there's a lot of work going on now that people, many applications, many services have to deal with large amounts of data and also being distributed across data centers and many different locations. Now, is it easy to do? Obviously, if you do something like this, there's an awful lot of very interesting questions popping up. Can you do it as I said before, soft state storage? What does it actually mean? Data discovery and routing. Now, sort of contemplating, you obviously, to make something robust, you want to duplicate things in many different places. Talked about consistency. Then the whole thing, trust and security, is the security alone is already a big issue. We have some ideas on how to do it. It's not really clear on how to implement it. And then obviously economics, and there's lots of interesting legal issues as well. All right, mobility, not going into that one. So this is just the last slide. If you actually do this is actually a slide I used I found in my old WINLAB slides. I did that 7-8 years ago. If you have this loosely coupled, it's basically you have a completely different way of doing distributed computing. It's not sort of like the classical that you basically this sort of passing messages across the commands that some entity is sending a request to some other entity to do something and send back a reply. If you do this around this sort of space, you almost think, it almost looks like we humans do, that you sort of express a desire to have something happening, or you ask somebody to do something for you, and maybe they're doing it at some stage in the future or not. And so this loosely coupled thing is in a way much more complicated, but on the other hand, most loosely coupled systems are a lot more robust. They may not ultimately do what you want, but at least they're robust. Okay. Sorry for meandering around a bit. But as I said, I'm really interested in new abstractions as really provided, and with it, new services provided by the network, by a truly distributed environment, which are much more meaningful to application and service developers than they are today.